Hello everyone, welcome back to my YouTube channel. So in today's video, we will understand an important theorem of a group theory in a very simple and step-by-step way. So if you are studying group theory and you feel that kernel is confusing or you feel that this proof looks difficult to you, so don't worry, because in this video I will explain each line clearly. So please watch the video till the end. So let's see the theorem first. Theorem says that let f define G to G dash be a homomorphism with kernel K, then f is 1 if and only if kernel has identity element. So what this theorem is saying, that if there is a f which is defining from a group G to its codomain group G dash, and it is a homomorphism and it is containing one kernel inside it, right? So f is 1 f is injective if and only if what its kernel has identity element. So this means that the function is injective when the kernel contains only the identity element. So before proving this theorem, I will tell you how we will prove this theorem, right? So we will divide this proof into two parts. The first part, we will assume that f is 1 f is 1 and I will show that kernel contains only identity element. In second part, I will assume that kernel contains identity element and I will prove that f is 1. So we are proving this theorem in two parts. In first part, we are taking f as 1 and we will prove that kernel contains only identity element. In another part, that is second part, we will assume that kernel contains only identity element and we will prove that f is 1. So let's see. So let's prove the part 1. So in part 1, firstly, I will tell you the definition of kernel. So kernel says, kernel of f, we are taking this f. So kernel says if there is an element x that belongs to G, right? There is an element x, we are taking an arbitrary element x which is belonging to G, such that image of this element x is equal to E dash. Now you might be wondering that what is E dash? So E dash is the identity element of E dash, G dash. So here E dash is what? E dash is the identity element of codomain of group G, that is G dash, right? So we are taking an element x that belongs to G and its image is equal to E dash, that is the identity element of G dash. Now clear what is the definition of kernel? Now we will take an element x. We are taking an element x that belongs to this kernel f. Now if I am taking an element of kernel f, why I am taking this element x of kernel f? Because I want to show that x is an identity element. So I have taken one arbitrary element of kernel, that is x. Now what I will do is, according to this definition, I can write fx is equal to E dash, right? Why? Because I have seen that images of images of elements are equal to identity element of G dash. So I can write this now in another equation. Here I am taking, we know an important property of homomorphism, that identity element image is always an identity, right? This is an important property of homomorphism, that important property of homomorphism. So that it means that the image of the identity is always an identity. Now from these two equations, I can see that fx is equal to fe. Now already we have assumed here, before proving this part, we have assumed that f is 1. This means that if their pre-images are equal. If elements pre-images are equal, then elements are also equal. So we can write x equal E. So here reason I can write this, since f is 1 1, so equal images give equal element, right? So I have written this. So here I have proved that element x is equal to E. This means that identity element is equal to x. X is what? X is an element of kernel. So here I can write, so the kernel contains only identity element. So part 1 is proved. Now we will take another part. This is second part. Here we will assume K contains identity element. ठीक है? And we will prove that f is 1 1. So we are taking two elements, arbitrary elements. We are taking a comma b, that is belonging to group G. Let a comma b belongs to G, and here let a comma b belongs to group G such that images of these two elements are equal. Okay, I am taking that there are two elements which belongs to group G, and these images of these two elements are equal. Now I will cancel out this FB. So to cancel out this FB, I will multiply both sides by FB inverse. So multiply by FB inverse. When we multiply FA with FB inverse and FB with FB inverse, here this will become identity, because if we are multiplying an element with its inverse, it will give identity. So using the homomorphism property, we know the homomorphism property that f a star b is equal to f a f b. So here this is given what? F a f b inverse. So we can write this as f a b inverse, right? So this is equal to E des, right? This means that AB inverse also belongs to kernel F. Why kernel F? Because here E des is identity element, and we have seen the definition of kernel in earlier in part 1. So here I can write that AB inverse belongs to kernel F. This means that I can write this as AB inverse is equal to E. Why? Because we have assumed here, kernel is equal to identity element. So I am writing here, I have taken that kernel is equal to identity element. So I am keeping this as equal to E. So here I am transposing B inverse from left hand side to right hand side. A is equal to BE, and multiplying an element with identity gives that element only. So here we can write A equal B. This shows that if two images are equal, this shows that if two images are equal, then their pre-images are also, then their elements are also equal. So in final conclusion, I will write, we have proved both parts. So therefore, a homomorphism is 1 if and only if its kernel is identity element only. Hence, proved. So if this explanation helped you, please like the video. If you have any doubt, write it in the comments because I will reply. Subscribe to the channel for more easy and clear mathematical videos. Thank you. Thank you so much.